Hey team, this is your tutorial on addition and elimination reactions, and we're going to start off by addressing how do addition reactions actually happen with alkenes, just in general. So this is just a bit of recap. As you can see here, I've got this alkene. If I react it with any of these reagents to form either a haloalkane or an alcohol, what's going to happen is these double bonds are going to open up. This one over here, this top bond, is going to open up and move up here, as you can see in this diagram. And this bottom bond is going to swing open this way and open up over here. This allows a free bonding site in these areas. The double bond, as you can see, is replaced by a single bond. And this can form any of these molecules, organic molecules. But why is that double bond replaced by a single bond? I need you to understand the fact that carbon has 6 protons in the middle and 6 electrons in the shells on the outside. Specifically, on the outermost shell, we have 4 valence electrons, which has the ability to bond or share bonds with 4 different things, okay, to form a full outer shell, which contains 8 through the sharing of electrons. 1, 2, 3, 4, 5, 6, 7, 8. Cool. So that means carbon has the ability to bond to 4 other atoms. And so I want you to think of these bonds as possible parking spaces. And so if I am opening up one of the bonds and opening up one of the bonds over here, that means that if there's 1, 2, 3 bonds, each carbon has 1 more possible parking site to be able to be filled. And so that's why a single bond is formed, because carbon can have 4 things that it bonds with. And so if the double bond opens, we have a single bond that forms in place of that double bond, so that each carbon is bonded to 1, 2, 3, 4 things to have that full outer shell, which contains 8 electrons. So hopefully that makes sense to you. If it doesn't, please let me know. The next thing that we want to address is, may as well talk about elimination reactions. When we have an elimination reaction, it's when we have an organic molecule, whether it's a haloalkane or alcohol, which reforms the double bond. And so because carbon can only form bonds with 4 things, okay, these carbons will have to sacrifice one of their hydrogens so that there's only 4 bonds. And that's going to be more clear as we go on. And so I guess I want to focus on addition and elimination reactions. And these notes are nicely printed out for you. And so here we are. Let's start off with addition reactions. In an addition reaction, for level 2 organic chemistry, we focus on the creation of either haloalkanes or alcohols from alkenes, as you can see here. Whenever we react an alkene with a hydrogen halide, we will get a haloalkane. Did you know that when this process happens, you can actually get 2 types of projects? I was meant to say products. You get 2 different types of products. You get a major product and a minor product. And so a major product is basically something that is made in greater quantities, and a minor product is made in lesser quantities. So both can be made, but one is made in more quantities than the other. When you react an alkene with H2O, H+, and heat, basically you will get a major product of an alcohol and a minor product of an alcohol. And so these are the 2 addition reactions you need to focus on in terms of the production of major and minor products. Moving on, there needs to be a bit of a criteria for the formation of major and minor products. For alkenes to form major and minor products, the criteria is that the molecules, the alkenes, need to be unsymmetrical. What do I mean by that? As you can see here, this alkene is symmetrical because of this double bond being placed right in the middle of this chain. This alkene, however, is unsymmetrical because this double bond is placed towards the end of the chain. So the shape of this is quite unsymmetrical. Similarly, you also need an unsymmetrical reagent like HCl, H2O, things with different atoms. You cannot use any of these types of reagents. And so this is going to be made very clear on why this won't work. And I guess before we get there, let's talk about what is actually happening in an addition reaction. So when the carbon, which has the most hydrogens, gains another hydrogen, this will form the major product. The major product is made in more quantity. The other product is the minor product. This is formed in smaller quantities. It is formed when the carbon with the least number of hydrogens in the double bond gains another hydrogen. What does that all mean? Okay, let's look at this example so that we're being more visual. As you can see here, I've got an unsymmetrical alkene. So let's take a look here and see what's happening with this unsymmetrical alkene. This unsymmetrical alkene is reacting with an unsymmetrical reagent, specifically hydrogen chloride, which is a hydrogen halide. And so when we react it with a hydrogen halide, we know that we're going to form some haloalkanes. One of these is going to be the major, and one of these is going to be the minor product. So which one's going to be which? Well, let's have a look and see. I'm going to illustrate this for you so you can see clearly what's happening. When we take part in this addition reaction, the double bonds break open. This bond over here is going to swing out this way, and this bond will swing out this way. And so what's going to replace the double bond? A single bond, because carbon can bond with a total of 4 things. Let me just rearrange these guys so it's a little bit neater. And so you can see now that we've got 2 possible bonding sites. What are going to take up these spaces? Well, since we're reacting it with HCl, we can see that a hydrogen atom can bond in this bonding space or this bonding space, and the chlorine atom can also bond in either this bonding space or this bonding space. So we have 2 possible combinations over here. And so let's try one combination and see what type of product that forms. For the sake of this example, I am going to pop the hydrogen over here, and the chlorine can go over here. What type of product does this form? The major or the minor product? Well, according to my notes, we know that if the carbon, which has the most number of hydrogens, gains another hydrogen, this will form the major product. So if we look at the 2 carbons involved in the double bond, which one is the carbon which has the most hydrogens? This one has 2 hydrogens. This carbon in the double bond only has 1. So we can say that this carbon over here on the right is the rich carbon, and this carbon over here on the left side of the double bond is the poor carbon. And so according to Markovnikov's rule, when the rich gets richer, you will get the major product. So because this carbon in the double bond has gained another hydrogen on top of the 2 hydrogens it already has, the rich has gotten richer, so this is the major product. Okay, so now let's try the next combination with this other haloalkane. Again, let's swing open our double bond and replace it with a single bond. I'm going to neaten it up again so everything is nice and tidy in terms of spatial arrangement. There are 2 bonding sites available. This time I'm going to put the hydrogen over here, and I'm going to put the chlorine over here. So in this instance, this is the rich carbon, this is the poor carbon. the rich carbon did not get richer in hydrogens. It gained a chlorine instead. So that hydrogen went to the other carbon, which was the poorer carbon, because it only had one hydrogen initially. Okay, and so this forms the minor product. This forms the minor product. And so this is the difference between major and minor products. Okay, and so there we have it. This is how you can distinguish what the two different products are, as long as you're reacting it with unsymmetrical alkenes and reagents. This does not work with symmetrical alkenes, and I'm going to show you that in a minute. So this is another example. I thought I might go through it because in this case, we are dealing with this reagent over here. And according to my notes, when you're reacting an alkene with H2O, H plus and heat, you're forming alcohols, okay? Because the O from this H2O group and the H as well is going to form an OH group, which can attach on to one of the double bonds, okay? And the other H, or any remaining H out of this reagent, can bond onto another carbon in the double bond. And you're going to see how. I'm going to show you. So what I'm going to do is I'm going to open up this double bond, and so this top bond can swing out here, this bottom bond can swing out here, and then what happens is we're replacing that double bond, which is opened up, with a single bond, because every carbon has to bond with 4 things. And I'm just going to get rid of these H's to neaten things up again. Cool. And so now, out of this reagent over here, I'm going to extract an O and an H, an OH group, and an hydrogen atom, okay? And so again, there are 2 possible bonding sites that this OH group can bond to, and there are 2 possible bonding sites that this H group can bond to, okay? And so let's try out one of the combinations. I'm going to pop the OH group over here, and the H atom can go here. Let's see what type of product is this. Is it a major product or is it a minor product? So remember, if the rich carbon in the double bond gets richer with hydrogens, it is going to be the major product. So in this example, if we look at 2 of the carbons in the double bond, this might seem repetitive, but it's all good revision. This carbon over here has 2 hydrogens. This carbon over here has 1. So this carbon on the right, this carbon on the right is the rich carbon. This carbon on the left is the poor carbon. And so here we have it. We see that the rich carbon has gained another hydrogen on top of the 2 it already has. So the rich carbon got richer. So this is our major product. Right, so this other option or product is going to have to be the minor product. So let's go ahead and draw that. Again, let's open up these double bonds. And there are 2 possible sites that OH can go on. Because last time I added the OH over here, this time I'm going to add the OH group over here. And then in this position, in this bonding site, I'm going to add the H in this carbon. So the rich carbon, we know that it was this one. Did it gain another pure hydrogen atom? No, it gained an OH. So the rich carbon did not get richer. Instead, the hydrogen went to the poor carbon. And so that's why this is the minor product. You only form the major product when the rich carbon in the double bond gets richer in the addition reaction. Cool. So now I want to go over this in a little bit more detail. As you can see here, this is a symmetrical alkene. This is an example of a symmetrical alkene. Let's try see if we can get major minor products. So here we are. I'm going to get this black pen, draw an arrow to show that this is what it's turning into. I'm going to redraw this molecule, this alkene, over here. I'm going to open up these double bonds. And I'm just going to stick them out here and replace this with a single bond. And so now I've got 2 bonding sites. So what's going to bond onto these 2 bonding sites? Well, it can either be the H or it can be Br. I'm going to bond H over here and Br over here. Okay, cool. That's one combination. Let me draw the other combination over, I'll just draw it here. Let's just pop it there. Okay, so instead of having the H here, I'm going to have the H here and the Br over here. Which one is the major? Which one is the minor? The answer is none of them. Why? Because if we're trying to look for the rich carbon that got richer in the double bond, as you can see here, these are the 2 carbons we're comparing. This carbon here has 1 hydrogen, and this carbon here has 1 hydrogen as well. So there is no rich carbon or poor carbon because both carbons have the same number of hydrogens, which is why we don't have the option of making a rich carbon richer, because there isn't one. So that's why you cannot get a major minor product out of a symmetrical alkene. You can just get 2 isomers, structural isomers, and we've covered that in the previous lesson. Go watch that video if you need recap on it. But you can't get major minor products because there's no rich carbon. Okay, another type of example. All right, we're dealing with an unsymmetrical alkene. This time we're reacting it with a symmetrical reagent. And so let me show you what would happen if we tried. This time I'm going to put the arrow this way just because we might bump into something there. But I want you to make your arrow straight usually. Anyways, so I'm going to redraw this molecule, open up that double bond over here. And so I've got 2 free bonding sites for 2 Br atoms. So 1 Br can go over here and 1 Br can go over here. Even if I were to swap these around, let me swap it around. What do you notice? Absolutely nothing has changed. And so because of that, there is no carbon which is gaining or losing any hydrogens. And it's all about hydrogens, remember? And so because we're dealing with a symmetrical reagent, there is no loss or gain of hydrogens, no rich carbon getting a hydrogen. We're only dealing with Brs, okay? And so it doesn't give a major minor product, again. So that's why it's important to have unsymmetrical reagents and alkenes. That's the requirement. So that's something that you can keep in mind. Cool. Now that we've focused on addition reactions on the left side of this whole page, we can now focus on elimination reactions. So the difference between elimination reactions and identifying what is the major product, okay, instead of rich getting richer being the major product, in elimination reactions, it's the poor carbon getting poorer in hydrogens, which makes up the major product. What does that mean? Well, before I get there, I want you to understand that when we're dealing with elimination reactions, it's going to be from haloalkanes turning into alkenes, as you can see over here, with the reagent of alcoholic KOH. And then we've got alcohols turning into alkenes, with the use of concentrated H2SO4 and heat. And so we're getting forming a double bond by getting rid of hydrogens. And so let's have a look at an example to see how a major product is formed. So here we are, we're dealing with an alcohol, and we know that we're dealing with an alcohol because of the presence of an OH group. The two carbons that we're going to be focusing on are going to be the neighbouring carbons to this alcoholic carbon. Okay, so we're looking at the alcoholic carbon's neighbours. So before we go ahead, okay, let's identify the rich carbon and the poor carbon on either side of the alcoholic carbon. Let's look at this one. This one over here, how many hydrogens does it have? It's got 1, 2, 3. How many hydrogens does this carbon have? It's got 1, 2. So this carbon is the rich carbon. This carbon is the poor carbon. All right, according to our rule, we know that if the poor carbon gets poorer, it is going to form the major product. That means if the poor carbon loses more hydrogen, then it's going to be the major product. So let's try and establish that or achieve that. Here we are, we're reacting the alcohol with concentrated H2SO4 to form an alkene. So let's focus on this molecule, this product here. I've removed and eliminated the OH group because this is an elimination reaction. And then what I'm going to do is I'm going to show you what is happening to this bond over here. It's got two possible places where it can flop onto to form a double bond. It can either go this way or it could go this way. Okay, and depending on which way it falls, will form either the major product or the minor product. I am going to flop this bond over here onto this left-hand side carbon. So I'm going to do that here. Cool. So I've formed this double bond with this left-hand neighbour. Okay, and so as a result, whenever a double bond is being formed, something has to be sacrificed. And what is going to be sacrificed? It's going to be a hydrogen. But which one? Well, it's going to be the one that is bonded to a carbon with way too many bonds around it. So if we look at this carbon here, let's see how many bonds it has around it. It's got 1, 2, 3, 4. So it's happy. We don't need to sacrifice anything from it. Let's look at this carbon, which has just been formed within this double bond. It's got 1, 2, 3, 4, 5. It's got 5 bonds and carbon can only have 4. So I am going to have to sacrifice one of the hydrogens. I'm going to sacrifice this one and the bond. So now it has 4, okay, bonds around it. As you can see, that carbon was the poor carbon, and due to the formation of a double bond, it has lost that hydrogen. Because the poor carbon lost a hydrogen due to the formation of a double bond, this is going to be the major product. Okay, so in elimination reactions, when the poor gets poorer, this is the major product. In an addition reaction, when the rich gets richer, that is the major product. And you need to understand that difference. Let's go ahead and look at this product here. This time I'm going to flop this bond and form a double bond between these two carbons. So let's do that. Boom. Okay, I'm just going to make that a little bit neater. Going to take that off, form it there. Okay, so now we've got to make sure that a hydrogen is being sacrificed as a result of this double bond formation. This carbon here, this one, has 1, 2, 3, 4 bonds, so it's happy. We don't need to sacrifice any hydrogens from it. But what about this one? It's got 1, 2, 3, 4, 5, okay? And so we do have to sacrifice a hydrogen from it. I'm going to take away this one here. And so as we have established, this was the rich carbon, and because it has lost a hydrogen due to the formation of a double bond, Since the rich had to sacrifice a hydrogen, this is the minor. And the reason why, I'll say it the other way around, it's because the poor didn't get poorer, it was the rich that got poorer. And during an elimination reaction, let me repeat it once again, the thing that forms a major product is always going to be the carbon, the poor carbon, which gets poorer, okay? And always remember, it's going to be the two carbons on either side of the alcoholic carbon, which you can form that double bond with and are comparing in terms of rich and poor, okay? Cool. So that's that. We have worked with that example. Feel free to pause the video and see if you can do this one. This time we're reacting a haloalkane, and we know it's a haloalkane because of the presence of a Cl group. We're reacting it with alcoholic KOH to form an alkene. Take a pause, see if you can do it yourself. Okay, before we go further, now that you're back and have given it a go, let's establish our rich and poor carbons. And so, remember we're focusing on the carbons which are neighbors to this halogenated carbon over here, okay? And so, let's go ahead and establish what's what. We can see here that this carbon on the right has 1, 2, 3 hydrogens, so it is going to be the rich. And then we've got this carbon, this neighboring carbon, has 2 hydrogens, so it's going to be the poor. Let's see what are the products that we can form. This bond can go 2 ways. It can either go here or it can either go here. Okay? And so let's look at the first molecule. Because we've formed a double bond with this carbon over here, it is going to have to sacrifice a hydrogen so that there are 4 bonds around this carbon. This carbon's pretty happy, it's got 4 bonds around it already. We know that this carbon here was the poor carbon, and because it experienced a loss, it got poorer in hydrogens. We know if the poor gets poorer, this is the major product. Over here, we've got a double bond forming between these 2 carbons. That means in order for this to be accurate, we've got to remove one of the hydrogens of this carbon because it used to have 5, now it has 4. We're all happy now. And because the rich got poorer, this does not meet the criteria of poor gets poorer, so this is the minor product. Cool. And that's basically that. This is another example. Okay. And so let's go ahead and try this out. In this case, we're dealing with this chlorine atom bang smack in the middle. I wonder if we can get a major or minor product out of this. So let me just redraw this over here. And so, because this is an elimination reaction, when we react this haloalkane with alcoholic KOH, we can get rid of this chlorine, and now we've got this bond that can go 2 ways. It can either go this way or this way. Let's see what happens. I'm gonna make it go this way. So, because these are the 2 carbons that we're focusing on, because we've formed a bond with this left-hand carbon, it is going to have to sacrifice a hydrogen. So how do we know if this is major or minor? Well, if we look here, let's look at the neighboring carbons. This carbon here has 2 hydrogens. This right-hand side carbon has 2 hydrogens as well. So which one is the poor and which one is the rich? None. There is no rich or poor carbon. So there is no such thing as the poor getting poorer because not one carbon is poorer than the other. So we can't actually form a major minor product. We can just form two different isomers of one another, okay? And feel free to go ahead and draw that. But this is what happens when you react something that is symmetrical. You cannot actually get major minor products. You can only get isomers, okay? And so that basically concludes this lesson. Use this to answer the questions that I've given you in class, and also apply this knowledge to past exam questions. No Brain Too Small has some amazing resources where they've collated all these types of questions together to get more practice and exposure. So go ahead, hope this tutorial has made sense. Please email me if you have any questions. See ya.